Okay, I wanted to talk about a complete mission concept. Fazil just talked about the trajectory. Joe talked a little bit about some of the work we did with the deformation, and you also heard from Dan Shears about the deformation. This work came out of essentially three different efforts. One was a small mission planetary study, a NIAC study, and some summer students that were around the lab. So the objectives to go to Apophis during the 2029 encounter are to understand the geology of the body, the rotational state, its interior structure, what happens in terms of tidal deformation, and more generally about the origin and evolution of small bodies, and to understand a potentially hazardous object and how it would potentially threaten the Earth. So we looked at a bunch of different mission concepts. For the studies, we identified a reference payload, designed a mission spacecraft around it, and looked at the risks. And as I said, this work came out of three different sponsors. You've heard about, Rick talked about Apophis a bit. It's on the order of 400, 200, or 300 to 400 meters in diameter. It has a spectrum that is suggestive of a unweathered object, and the question is what happens with space weathering. The shape model that was used was Marina's radar model. So as I said, the specific objectives now were to determine the rotational state and bulk properties, the mass and interior structure, and the geology and the tidal effects. So a lot of this was based on the idea that we would carry a seismometer that we would deploy on the surface and understand what's going on in the interior, both during the encounter with the Earth and over a longer period of time. And then there were a number of secondary objectives that sort of fell out of the instruments that were required to do the level 1 objectives. So you can do a complete study of the object. Fazil just talked about this in a lot of detail, so I won't go over it. The key points are that there are a number of different ways to get there, depending upon whether you're trying to do a small mass on an ESPA ring or whether you had a dedicated launch. In this particular version for the ESPA ring, we can park at one of the Lagrange points and hang out until we're ready to go to Apophis so that we're insensitive to any slips in a launch date. And then we go on from there. The idea was to arrive sufficiently early that we could map the entire body, deploy the seismometer before we got to the encounter, go through the encounter, and then essentially remap the body after the encounter so that we could detect any changes that may have occurred. So we want to understand something about the surface character and any modifications. It's been suggested that tidal encounters between small bodies and large planets can generate surface movement, which would lead to some of the observations of relatively unweathered surfaces on these bodies. If you've got a body just sitting there for 4.5 billion years, it should be space weathered, and you shouldn't really see any changes unless you had a small impact or something occurring on the body. But the tidal interaction may expose some fresh material, either downslope or because of seismic movement. And so we wanted to map the body to understand what happens there. Next one. Oh. Is it time delay here? Okay. The other part we wanted to understand was the seismology. This is some work that Nick Schmer from across the street did. He's got a poster tonight. Basically, we looked at the idea of what happens in terms of sampling frequency and energy dispersion. He looked at a situation where there was an energy input at one end of the body and watch how it propagates. The second rendition down here shows what happens if you have an event, a seismic event, in the interior of the body. One of the key problems with this is the irregular shape of the body winds up scattering energy all over the place, and you get multiple reflections and diffractions, and so you're going to get a very complex waveform out of the seismometer if you were to observe such an event. We assume that in terms of seismic activity, if in a sort of passive experiment, you would see micrometeorites. We're going to be there long enough that we would expect to see an impact or two that were large enough to generate seismic energy. You would presumably see thermal cracking on the surface due to the thermal fatigue, just like we saw on the moon. You might expect to see some kind of deformation during the tidal encounter. And again, it depends on how much that turns out to be is going to depend on the internal structure and the Young's modulus and cohesion and a number of things about the particles. The other opportunity would be to do an active experiment where not only do we deploy a seismometer, but we deploy an energy source. Joe talked about this. The key point here is that the amount of deformation that's going to occur is unresolvable in an image. However, the changes in the pole rotation and the periodicity of the rotation can be observed. If we're sitting off the body by a few kilometers, watching it go through its encounter, we can take images with a high enough cadence that we can watch the changes occur and watch the changes in rotation period as they occur. So the spacecraft we came up with, as Fazal just mentioned, we use SEP. In this particular implementation, we had a requirement to try to get down below 180 kilograms. We didn't get there. We got to around 228 on the basis of the wet mass. But what it indicates is that for a relatively small scale spacecraft, you can do such a mission. This is the antenna. This harpoon on the top is our seismometer. This is the interior of the spacecraft. As Fazal said, it's a SEP, so we had a propellant tank here, a bunch of internal electronics. There are two other experiments. There's an imager, which is down here, and the seismometer that we're going to deploy. The solar panels extend after launch and generate 700 watts of power. We had a relatively simple RGB camera to observe the body, and what we would do is conduct a range of imaging campaigns so that we could look at the whole body over the course of its rotation. Since we don't know exactly what the orientation is right now, the point of arriving early is we could observe the whole body regardless of where the pole is oriented, although we may have to wait a while depending upon where the pole is, but we get a complete image before the encounter and then again after the encounter. And we use some other images to understand what's going on right during closest approach. The assumption we made was that Apophis is going to look something like Itokawa in terms of not necessarily the shape, but that there will be areas where there's really fine-grained material, and there's also going to be areas of rocks. So the seismometer looks something like this. It uses a liquid-filled, in this particular implementation, where the motion of the ground generates a current as the fluid goes back and forth through the electrodes. This is orientation independent. It doesn't have to be leveled. So we would imagine this harpoon part sticking into the surface, batteries to run it, and electronics. This is essentially a small independent spacecraft. We're going to stick this in the surface and then leave it there. The way we would stick it in the surface is a challenge. In this particular implementation, we were going to use an extendable arm and then make a close approach to the body and then try to stick this thing into the surface using the force of the spacecraft and let go. The particular challenge here is making sure you coordinate your velocity relative to the body so that you don't have any torques on the thing. It does give us the opportunity, though, to make an attempt to deploy it. If it doesn't work or if things aren't going well, we can back off and then try it again. But presumably we could be successful at some point and put this thing in, let it go, and then the spacecraft would back off. During the course of the mission, the seismometer would talk to the spacecraft, and the spacecraft would talk to the Earth. So the summary of this is that we can do important science. It's a unique opportunity to study the tidal interactions with a large body. Because it's close to the Earth, the communications is not particularly an issue. Because it's close to the sun, power is not an issue. There are multiple launch and rendezvous opportunities. And all things considered, it's a relatively simple spacecraft. There are some challenges. CONOPS at a small body that has essentially no gravity is an issue, but with the experience of NEAR and Rosetta, Hayabusa, and OSIRIS-REx, we're beginning to understand how to do that. Touching the surface is also a challenge. Hayabusa and OSIRIS-REx have touched the surface and collected samples, but they didn't try to put anything into the surface where the relative velocity would be an issue. So that's a particular challenge, is how we would actually conduct that. Thank you.
Okay, we have time for questions. Well, I have one.
Okay.
Do you think that active seismic experiments should be considered more in general for small body missions, or that is something that makes more sense for a case like this when you have such a close approach?
Yeah, I think so. We looked at what it would take to generate enough energy. And all you really need is one of these NASA initiators, which they use for, separating stages and stuff. It's a small thing. It's a relatively well-known technology, and it's not going to impart enough of velocity to change the trajectory. The key is that we couple both the seismometer and that charge to the surface.
Just curious, since you're mass limited with just a seismometer, if you were to imagine putting a pinger or a transponder on this asteroid, how much mass would you add, do you think, to get a good long-lived transponder attached to it?
I think a few kilograms would be
Oh,
sufficient.
okay, so it's not a major.
This particular implementation, actually, one of the conclusions we reached was this is not the way to do it. It should be done in a discovery class kind of mission where you could actually have multiple seismometers and energy sources, and you could carry a pinger or some other something else.
You'd have mass budget for such.
Yeah. So in a discovery class, we have plenty of mass margin.
Yeah. And I'd just add that Apophis is interesting just because of its intrinsic nature and its overall long-term hazard. So I think it's a great destination just on its own merit. The encounter gives that extra potential, but then you can also carry that active seismic experiment in case you go by the Earth and it's radio quiet there. Then you can do your deploy your active experiment post facto after it's long past the Earth.
Yeah, well, we would arrive sufficiently early, we would emplace it, and we'd have a background, go through the encounter and continue. And effectively, there's no reason why we can't continue.
We have to move